Hello and welcome back to Summer Work Help for Calculus 1. In this video, we're going to be taking a look at question number 8. So question 8 says, write an equation for each graph below. So for both A and B, we have a graph and we're looking for an equation. So let's get into it. 8A. So for 8A, we definitely want to be in a position where we can recognize that this is a parabola, right? So I'd say at a minimum, we want to be able to recognize this is a parabola. Also at a minimum, we want to know that a parabola is the graph of a quadratic function. Really want to know that. So we're looking for the equation of a quadratic function. And one thing I'm noticing in this picture is, we have some information, right? We have this point right here, very important point on any parabola. This is the vertex. That's helpful. And then we have sort of this like random point, 3, -5. That's good information to have. It's not like there's nothing really special about that point. We are going to need that point in order to complete this question. But it's good that we have the vertex. What we don't have is we do not have our x-intercepts. And we don't have our y-intercept, which is like down there somewhere, right? So we don't have our intercepts, but we do have the vertex. Because of that, we have to be kind of smart about like what form of the equation of a quadratic function do we want to use, right? One way to write a quadratic is like this, right? This is like standard form for a quadratic. This is the form that your quadratic needs to be in if you want to use the quadratic formula. But I don't have any idea how we're going to get that from the information that we have here. Another version of a quadratic looks something like this. Not the same B's and C's, mind you. These are different A's and B. Well, not different A, but different B and a different C. But without the x-intercepts, we can't really get that, right? Because in this case, in the second one, the values for B and C, those would be our x-intercepts, and we don't know them. So none of this is really going to work, right? So I'm going to get rid of it, right? So trying to go that route is not going to be that helpful. What will be helpful is, well, we're given the vertex. There is a form of a quadratic equation called vertex form, and that is y minus, or no, not y1, thinking of something else, y minus k equals a parentheses x minus h squared. All right. This is the vertex form of a quadratic function. Sometimes, as we've seen, sometimes the k is moved to the right, where it would be y equals a parentheses x minus h squared plus k at the end. They're the same thing, they just look different. That form is useful if you want to get y equals and you want to graph it, whatever. But I'm going to use sort of the standard form of vertex form, which is this. So in order to really answer this question, what we need is our vertex, which is located, so actually I'll write it over here. The vertex in vertex form is h comma k, right? And then our vertical stretch is our value for a. So all I really need here are 3 numbers. I need h, I need k, and I need a, and I'm basically done. If I'm looking for h comma k here, h is my x coordinate of my vertex when they tell us that's 5. Okay. K is my y coordinate for my vertex, and they tell us that's 7. That's great. Like, they're kind of doing the work for us. So all I need now is I need my vertical stretch, which is A. So the vertical stretch, this is where the other point kicks in, right? So far we haven't really used the 3, -5, but the vertex certainly tells us a lot of information, but the vertex is not going to tell us what the vertical stretch is. So I need to find the vertical stretch. Now, here's where kind of knowing some of the sort of the general some of the general characteristics of a parabola can be kind of helpful here. First of all, we need to recognize that this is an upside down parabola, right? It's going down, right? Everyone can see that. So what that means is because it's pointing downward, it means that A has to be negative. So A is less than 0. All right, so we've narrowed it down to being a negative number, but now we need to figure out what is that negative number specifically. So with a, I'll do this over here as kind of like a sidebar. We'll do this. Okay. It's important to know a couple of, I think, what are called anchor points on a parabola. On a standard parabola. See if I can do the other half a little bit better here. All right, that's good enough. Okay. It's important to know sort of how a couple of points relate to each other on the parent function. When I say the parent function, we're talking about y equals x squared, right? The most basic possible parabola that you can possibly have, y equals x squared. From the vertex, which in this case would be 0, 0. From the vertex, if you go to the right 1 unit, you're at 1, well, the y value is going to be 1. All right, so 1, 1 would be on the parent function. Okay. If you go over another unit, you're at 2. And if you go up, you're going to be at 4. So 2, 4, because 2 squared is 4. And then at 3, I guess we'll just extend it a little bit. Now we're up here. At 3, you're going to be at 9, because 3 squared is 9. Like that. This is good to know when it comes to sort of like how does a parabola sort of like normally function when there is no vertical stretch, because in this case the vertical stretch is 1, right? So in a quote normal parabola where like nothing has been altered or changed, just sort of notice what's happening here as you go away from the vertex, right? So as you go away from the vertex, when you go 1 unit away, your y value changes by 1. When you go 2 units away, your y value changes by 4. And when you go 3 units away, your y value changes by 9 from the vertex. Okay? And that's going to be important to sort of understand, well, what's the vertical stretch for like any other parabola? So if I look here, my vertex is at 5. My x coordinate here is 5, and then the other point that I have is 3. Okay, so that means I'm at 5, and then this was 4, and then this is 3. Okay, so I've gone from 5. I've gone over 2 units. So I'd encourage everyone to take a look at that and just make sure that you can see that from the vertex, the other data point that I have, my vertex is at 5, and then for my other data point, my x value has changed by 2. So change of 2. In the parent parabola, when my x value changes by 2, my y value changes by 4. But in this case, my y value was 7 at the vertex, and it changed all the way down to -5. So what's the change in y? How much did y change going from 7 to -5? Well, 7 and -5, those are 12 units apart. All right. So when the vertical stretch is 1, so over here my vertical stretch is 1. When the vertical stretch is 1, you would expect the y value to change by 4 units when your x units change by 2. In this parabola that has some vertical stretch to it, when the x value changed by 2 from the vertex, my y value changed by 12, not 4. So if you think about, well, what do you have to do to 4 to get 12? Well, what's happened is this has been stretched by a factor of 3. Okay, so every change in x, the resulting change in y has been scaled. It's been multiplied by a factor of 3, because when I changed by 2 units, I saw a change in my y value of 12. Going from 5 to 3 resulted in my y value from 7 going to -5, so it changed by 12. And again, it's negative because it's going down. So for all of those reasons, okay, for all of those reasons, I'll just continue this. My a value is -3, because that's how much the y values have been stretched. So now I have all the information I need to write my equation. So my equation in vertex form is going to be y minus the y value on my vertex, which is 7, equals the vertical stretch is -3. Again, it's negative because it goes down, and it's 3 because all of the changes in y that you would expect, they've all been stretched by a factor of 3. Parentheses, x minus the x coordinate of the vertex, which is 5. And don't forget the squared. If you don't write the squared, it's not a parabola, it's a straight line. Right? It would look like point slope form of a line. So you need that squared on the x minus whatever term to make it a parabola. So that's it. So clearly, for 8a, I would say that, kind of the hardest thing is getting the vertical stretch. They give you the vertex. So because they give you the vertex, you got to use vertex form, right? That's easy. That's relatively easy, I would say. It's also relatively easy to see that the vertical stretch has to be negative because you're going down, but then actually getting the number itself of 3, I think, is kind of where that problem gets a little tricky. So final answer for 8A. 8B. So 8B is, pretty different kind of question from 8A. So with 8B, first of all, this is clearly not a parabola, right? So it's not a quadratic. It's also not a cubic. A cubic, what's called the end behavior, with a cubic, they go in different directions. So either with a cubic, either it starts by going down and then goes up, or it starts by going up and then it goes down, right? That's kind of what a cubic looks like generally. So this is not a cubic function. This is clearly not a linear function. It's not a quadratic function. So it's one more than that. This is a quartic function. So it's a degree of 4. And maybe you haven't had that much experience with quartic functions, and that's okay. You can actually still get the equation just by sort of understanding like how functions work and how the graph of functions work and like what's the information that they tell us and stuff like that, right? So even if you have not had much experience with quartic functions, I would still encourage you to try to answer this, because it's a good opportunity to sort of connect the behavior of a graph with what's going on in the equation of a function. Right, and that's just good regardless of what it could be, a degree 8 function, right? For all I care, right? So there's just certain ways that graphs and function and equations kind of relate to each other. So if you take a look at this graph, right off the bat, you can see that they give us the y-intercept, right there. So I'll just make a note of that. So I'll write it down here. So the y-intercept is 12. Okay, good. They also give us all of the x-intercepts. I'll go say y equals 12. We'll just go ahead. So y equals 12. And then for the x-intercepts, my x-intercepts are -1, 2, and 3. Now, one thing I want to point out here is that these intercepts, they're not all like behaving the same way. Notice that with both 2 and 3, the graph, it's here, it's positive to the left of 2, and it hits 2, and then it dives into the negative, right? So it was positive, and then it hits 2, and then it's negative. And then likewise at 3, it was negative, and then it hits 3, and then it's positive. So the graph kind of goes through the x-axis, and it goes from quadrant 1 to quadrant 4, and then from quadrant 4 to quadrant 1. With -1 over here on the left, this is different, because what happens is on the left, it's positive, and then it hits -1, but then it doesn't dip below the x-axis. It kind of like bounces off the x-axis and then it goes and it's positive again, right? So you notice that, right? Because that actually matters. And the reason why that matters is that when that happens, when you have an intercept like this that kind of bounces off of the x-axis and doesn't actually go into the other quadrant, right? This graph does not go into quadrant 3, right? Quadrant 3 is over here. And this graph never touches quadrant 3. So because of that, this -1 is what's called a double root. And I'm going to show you kind of where that's going to show up in the equation, all right? So we really have like 4 intercepts here, except 2 of them are the same thing. It's like -1 twice almost, right? Is kind of how you can sort of unofficially think about that. So here's, if I wanted to write the sort of the information that we have so far, here is where we're at. Y equals. Now, there's some vertical stretch here. I'm going to call that A. It's possible, let me move this over. Y equals. Okay, so we have a vertical stretch of A. Now it's possible that A is 1. Now if A is 1, then there kind of is no vertical stretch and you don't really need to write the 1. But where I'm going to write the A there right now, and then I'm going to take all of my x-intercepts and I'm going to express them in factored form. So I have x minus my first x-intercept is -1. So I'm going to subtract a -1. And when you subtract a -1, it becomes just +1, close parentheses. Now I said that -1 is this double root because it kind of bounces like that off of the x-axis. And because it's a double root, I'm going to square it. So if you haven't seen that before, that's fine. I don't think everyone has seen that. But when you have a double root like that, you can express it as x plus or minus whatever, and then it's squared. I'm going to keep going with my other x-intercepts. So my next intercept was 2, so it's going to be x, and you subtract it, right? So -2, because when you plug in a 2, you want to get 0. So if you plug a 2 into that, you'll get 0. If you plug a -1 into that, you'll get 0. And then my last intercept was 3. So that's the progress that I have made with this problem so far, which means all that I'm missing is the vertical stretch. Okay, so I want my vertical stretch, and in order to get that, I think probably the easiest way to do that is going to now look at the y-intercept. Right? Notice that the y-intercept with any function, not just this function, but with any function, the y-intercept is what happens when x equals 0. Right? You plug in a 0, and then whatever you get is your y-intercept. So let's try doing that now, right? So the y-intercept is 12. So when I plug in, I'll start on the right-hand side here. I don't know what A is. I'm trying to get A. But I'm plugging in 0. All right, I'm letting x equal 0 because I know that when I do that, I get a 12. So when x equals 0, okay, I get 0 plus 1, which is 1 squared. Then I get 0 minus 2, which is negative 2. And then I get 0 minus 3, which is negative 3. Okay, I'm just letting x equal 0. And the graph says that when that happens, you get a 12. That is the result of plugging in 0 into this function. Well, now I have an equation that only involves a, and that I can solve with really not that much difficulty. So I'll just go kind of like left to right here. 1 squared is 1, times negative 2 is negative 2, times negative 3 is positive 6. So this becomes 6a, right? Because all the numbers to the right of a, they're kind of just like a coefficient, so I just move them to the left of a. So again, 1 squared times negative 2 times negative 3 is positive 6. So I get 12 equals 6a, divide by 6, and I get a equals 2. So my answer here, y equals, we have a vertical stretch of 2, and then we have a double root at negative 1, and then we have one like single root at not 1 but 2, and then I have my last root at positive 3. Just like that. And that is my equation for B. So again, even if you have kind of limited experience with quartic functions and graphs that look like this, they give you all the information you need, and it's just you just got to understand sort of like, all right, well, if they give you the x-intercepts, how is that useful? If they give you the y-intercept, how is that useful? And how can I kind of apply that? And so it's a good question to see, you know, what is your understanding of the relationship between graphs and equations? So that is question number 8.